Everybody knows I stink at golf. Well, doesn't everybody? Okay. What we have in this problem is a golf problem. It's really a projectile motion problem, but it's with a golfer. And we've got a golfer, and they're teeing off on level ground. And when they hit the golf ball, they give it an initial speed of 42 meters per second and an initial direction of 35 degrees above the horizontal. And all we want to know in this problem is how far, so a delta x, a displacement, from the golfer does the ball land. So let's just draw a picture, okay? Here's the ground. Here's a golf ball, you know. And they go whack, boom, and the golf ball lands out here. We want to know how far away from them does it land. We want to know what this delta x actually is. And all we do know is to start the problem that this ball is initially hit with a velocity of 42 meters per second at an angle of 35 degrees. Oh, is that even enough information to solve this? Like, how do we do this? Of course it's enough information to solve this. We are physicists. So, before we even get into the mess that is the hitting the golf ball, let's just think about this real quick. There are a few things we automatically know for the box. We know that if we hit this golf ball up, it's going to fall back down, right? It's going to slow down its upward ascent, and then it's going to, descend more rapidly, which means that there's an acceleration here, and we know that acceleration is gravity. So negative 9.8 meters per second squared. We know that's the acceleration in the y direction. That's gravity. We know that after we hit the ball, nothing is like gonna fire turbo rocket boosters on the golf ball as well. It's a golf ball. Like, you hit it and now it's moving. That's it. So we know the x acceleration is 0. We just know that. Okay. What else do we know? Well, we also can say that when we hit this golf ball, the golf ball goes up and then it comes back down and it lands on the ground again. Now, if this is not in Pennsylvania where everything is a hill, it would land on the same level ground, the same height as before. And if that's the case, what's its displacement in the y direction? Well, it went up and then came back down. Has it gone anywhere? No. So we can say that in the y direction, our displacement is 0 meters. Okay? So that's what we can say right off the bat for a problem like this, which is kind of cool. So, how could we go ahead and solve this? Well, let's take a look at this triangle to begin with here. If I look at this initial triangle, I know that I hit the ball at 42 meters per second at an angle. And that angle at which I hit the ball was a ripping 35 degrees. If I break this 42 meters per second up into an x and a y direction, this down here, this is the velocity in the x direction. And this here is the initial velocity in the y direction. I don't know why I drew my V like that. I like to draw them curvy. So, can I solve for the initial velocity in the y direction or the velocity in the x direction? Sure I can. This is just a SOHCAHTOA problem here. This is a right-angled triangle. We can easily solve for this. If we go ahead and label our sides, this is our opposite, this is our hypotenuse, this is our adjacent side, and that means we can solve for everything just using the mighty chief SOHCAHTOA. If we want this initial y velocity, that's the opposite side, we know that the sine of 35 degrees, make sure your calculator's in degrees, I'm looking at you, Sydney, equals the opposite, VIY, over the hypotenuse, which is 42. If we multiply each side by 42, we find that the initial y velocity is, I got to calculate this now, 42 sine of 35, I get 24.09. So 24.09 meters per second. That can go in our box. That's the initial y velocity, 24.09. Woo! What is the x velocity here? Well, that's the adjacent side over hypotenuse. So we can say that the cosine of 35 equals the x velocity, and that's the initial and the final because there's no acceleration, divided by 42. Multiply by 42 on each side, so 42 times the cosine of 35, and we find out that the x velocity is a 34.40 meters per second. So we can go and put that in the box. And remember, because there's no acceleration and there's no air resistance, both of these are going to be 34.40. Okay? So let's see, what can we do now? Well, for the box, I need to have 2 out of the 3 known things, which is velocity is 1, delta x is another, and time is the third. I only have 1 of them right now. But I know that on the right side, the y, I just need 3 out of 5 to use my best friend. And I have that. I've got 1, 2, 3. So let's go and solve for time, because we know that if we solve for time, we can bounce it over. Then we'll have 2 of the 3, and then we'll be able to figure out how far from the golf where that ball landed. So let's just do that. We know the system we're setting up. Let's go do it. So let's see. If we can solve our best friend here, we have an initial velocity, a delta x, and an acceleration, and our time is what we're looking for. So I'm looking at equation number 5 again. If you haven't noticed, equation number 5 pops up a lot in projectile motion. This is why a few months ago I said I like equation number 5 the best. So equation number 5, if you don't know what we're talking about this equation. Delta x, or some people call this a delta y because we're on the y side of the problem. This just equals an initial velocity, and since we're on the y side, the y direction, multiplied by time plus 1/2 at squared. And that's the y acceleration or gravity. At this point, we can just drop in numbers like there's no tomorrow. Our delta x, or delta y, is 0, because that's what it is in the box. And our initial velocity here is, what was that? That was 24.09 multiplied by t plus 1/2 times negative 9.8 times t squared. Whew. Now, this may kind of look like a quadratic, and if you wanted to, you could use the quadratic equation here, but we're going to make things a little bit nicer so that we don't have to. I'm going to notice that I have a t and a t squared here. Both of these are t's, and since they both share at least one t, I'm going to factor a t out of this equation. Okay? I'm also going to multiply these terms together to get negative 4.9 so that I can rewrite this as saying 0 equals 24.09 minus, because there's the negative, this is going to be 4.9, and then t, and then here's the t I factored out. Because if I factored it back in, I'd have 24.09 t, and then that would be a t squared. Okay, so I just factored a t out. I could have 2 answers here, and that's what the quadratic will show you. One of the answers is if t equals 0. Because if t equals 0, this is going to be 0 times whatever equals 0. But I don't care about that, because this is a trivial answer. What it's basically saying here is, at time equals 0, your golf ball is on the ground. Yeah, because I put it on the tee, like I'm about to hit it. Who cares? I want to know when it's on the ground again way out here. That's what we're looking for, right? So if we solve this and set that equal to 0, that will give us our second possible time. So what we care about here is saying that 24.09 minus 4.9t equals 0. Because if I look at this and set that equal to 0, this will be true. The ball will hit the ground again. And now we can just solve this. Billion different ways to do this algebra, whichever way you like to see it first. What I'm going to do is I'm going to subtract the 24.09 to the other side. So I'm going to get negative 4.9t equals negative 24.09. And then when I divide by negative 4.9, divide by negative 4.9, I see that my 2 negatives divide out here, which is super nice. This means that the time I will have as my answer will be positive, which you need it to be positive. If it comes back as negative, that means you've gone backwards in time, which is like a whole nightmare. So what we have here is that time is 24.09 divided by 4.9, and that means our time here is going to be, let's see, 24.09 divided by 4.9. Our time is going to be 4.92 seconds. Okay, that's our time. So let's go back up, plug in our time of 4.92 seconds into both sides. And now, we're not done with the problem, but now we've got 1, 2 things on the left we can go solve for delta x. And the equation we use for that is always equation number 1 on our best friend, because we don't have an acceleration there. And that equation number 1, if you recall, is that a velocity equals a delta x divided by time, or displacement over time. To solve for delta x, we simply say it is a velocity multiplied by time. And in this case here, we know those values. We have to go grab them real quick. It's 34.4. So 34.4 meters per second for the velocity, multiplied by the time, which we just got as 4.92 seconds. Notice that the seconds are going to cancel or divide out, which is nice for us. And that will simply give us a delta x here of, well, whatever that is multiplied together, 34.4 times 4.92, a grand total of 169.25 meters. Okay, so that's how we can solve that. And if we wanted to, we could go back into our box and be like, ho ho, look at this, I am the greatest. 169.25 meters. Okay. Notice in this case, we didn't actually solve for the final y velocity. We didn't need it in this problem. But technically we know what it is already. If you recall, whenever we throw an object upwards with a velocity like plus 10 meters per second, when it comes back down to the same height, it has the same velocity, well, same speed, but a different direction, negative 10 meters per second. So if you wanted to, you could have recognized that this value here was just negative 24.09, and you actually didn't have to use equation number 5 here. You could have used VI, VF, and A to solve for t, and you could have gotten equation 3 out of that, which would have been a little bit easier. So that's, a full set there. Another way you could have solved this problem, if you're kind of recognizing it, maybe you see things a little differently, is you could have actually solved this problem halfway. You could have said that, hey, at halfway, my final velocity at maximum height in the y direction is 0. And then you could have used VI, VF, and A to solve for t, once again using equation number 3 for that. Once you solve for that time, though, this is the time to go halfway. So you would simply multiply it by 2, that time, to go the full distance. Okay? So you could solve problems like that as well. There's many ways that you can kind of like think about these things because they're symmetric across the middle like that, assuming no air resistance for these problems. But the big thing to recognize is that no matter what, you had to have started with this SOHCAHTOA up here. Okay? Whenever we gave you this initial velocity at some angle, that actually gave you a ton of information in our box for the x and y's, and then the other stuff is just natural physics things that we've known throughout our units. And if you can do that, and you can use your best friend, you can solve a billion different types of these problems going through there. And I think there's another video here on the YouTube page where I just give a random example of, maybe a soccer ball is being kicked at some random angle. Okay, so that's how we can kind of think about these and go about them. All sorts of different stuff you can do here, but just really think about what you have, fill out your box, and move accordingly. Okay, so for now, this has been finished. Adios, take it easy, and continue to do great physics.